I'm Trevor Houston. This is Andrew, Jackson, and Greg. We're Team 2, and this is our URC presentation. So starting with an overview of the build process that we took, as well as the typical process that some of the other teams took. Obviously, both of our bots look very similar. Without the hopper on the one on the right there, pretty much one-to-one. And we decided to take this process because it allowed us to have more time to kind of develop and perfect the design of one bot, and then transition that over to the other bot, as well as have more time to research and develop all of those systems overall within them, so that they were able to perform optimally when it came to competition. This is a look at our tournament strategy on the day. We're going to start with the 30-second autonomous period where both of our bots are going to perform the same routine. They're going to go to the opposite side of the field, back up into the match loaders, where, assuming we're on the red team, they will intake all 6 blocks and color sort out the 3 blue blocks. And then we will load an additional 3 match load blocks into our bot, where then they will drive up to the front of the long goal, score all 7 blocks that they have with the addition of the initial match load that they had, and then back up into the match loaders again, where we will then put in our final 3 match load blocks, and then they will end the autonomous period at the front of the long goals, where then we'll switch over to the driver control, and we'll have a decision to make where we can either score those 3 blocks in the long goals, depending on how many we were able to get in during the autonomous period. We can use our de-scoring hook to push the blocks into the control zone so that we're able to get that control bonus. And then we want to transition into the zone in the middle, where we want to prioritize scoring on the middle goals, as we found that a lot of other teams like to score most of their blocks in that area. So we want to try to maintain that. And then at the end, the last 20 seconds of the match, we're going to go down to the park zone, where we're going to attempt a double park. This is a look at the video. So this is a look at our highest skills day competition. This is still kind of the early stages of our autonomous routine, where we didn't have as consistent match loading. So we just focused on scoring the initial match load block into the long goals. And then when we switch over to the driver control portion, we start to intake blocks from the match loaders. We currently didn't have color sorting active on the bot with the red flap. So I have to kind of manually color sort out the red team's blocks. The other bot is going for the middle goal to try to get those control zones. And then moving back to the match loader, getting those 6 match load blocks that we didn't get initially in the autonomous period. Loading those up, attacking the other side of the long goal. And then towards the end, we're going to make the double park, as well as grab that control bonus. Using the de-scoring hook, grab that control bonus on the other long goal by moving it into the zone with the take. So we were able to achieve a score of 91 on this competition.
All right, so brief history of how our robots came to be. Our first main goal was to determine the shape and kind of flow of the block through the robot. So there are 2 main approaches that teams usually take, either a block type shape, which usually allows for a hopper, or a right triangle shape that some other teams will show off, where blocks go straight up the intake and will go directly out. There's no storage mechanism. We determined, based on our strategy that we developed, that we wanted a hopper to store blocks. So you can see in our first preliminary sketch, the intake rollers go up to to a decision point where there's an indexing roller that can take the blocks either into the hopper or store them on one of the goals. We then started prototyping with this, developing a preliminary intake system in hopper just to show off the idea. From there, we worked on scoring, mostly on the long goal, so that we could prove out our concept to make sure it all worked. We then stuck it on a drivetrain so that we could drive around, see what worked, see what needed improvement, see where positioning would be optimal. From there, we built up the hopper walls, allowed for a scoring flap on the top so that blocks wouldn't shoot over the goal, and started prototyping an intake flap so that we could get blocks out of the mass flow tubes. From there, we really played around with sensors, specifically the color sensor that needed some work with tuning, and a lot of 3D printed parts and tuning later we get to our final product. So for block scoring, we have the three main goals. First, the long goal, which makes use of this indexing roller at the top. When blocks are stored in the hopper, this motor up here will turn forward, scoring blocks at the top. Likewise, this roller can spin the other way to shoot blocks out the front. And the low goal can be scored by just getting blocks right out of the intake.
So, two of the main requirements for this project were to include a minimum of 3 sensors, where one of those sensors is a non-VEX sensor. Both of our robots include VEX limit switches, VEX inertial sensors, and our non-VEX sensor is a color sensor that I designed. The VEX limit switches are used in the autonomous period to enable autonomous scoring. The VEX inertial sensor is used in the autonomous period as well to facilitate autonomous navigation. Essentially, the inertial sensor is an electronic compass that allows the robot to make turns. The non-VEX color sensor that is designed to determine the color of the blocks as they're picked up. The color sensor is utilized in both the autonomous and driver control periods. The color sensor provides a digital output that allows the robot to decide if it should keep or discard the blocks. A brief overview of the circuit data design. Color sensor circuit is comprised of an RGB diode, 2 comparators, and a bunch of resistors. Color sensor circuit, essentially, the RGB diode acts as a color-dependent current source, which generates a color-dependent voltage on the analog front end of the comparators. When a red block is present, a large enough analog voltage is generated across the sensor resistors to trigger the red output button. This is also true for a blue block. When a blue block is present, a large enough analog voltage is generated to trigger the blue output button. Essentially, LEDs shine at the block and the light is reflected back at the RGB diode. Over here on the left is a PCB model that I designed that houses the circuitry for the color sensor circuit. On the right-hand side is the final color sensor in this enclosure. In the center is the RGB diode, and surrounding that are 8 LEDs that send light out and expect light to reflect back at the RGB diode. Along with the color sensor and our other sensors, our robots are products with many other moving parts. We provided a demonstration video here that demonstrates the color sensor working as well as the intake flap going down. In this video, the robot's configured to sort out blue blocks. As you can see, it's spitting out blue blocks, and it kept all the red blocks.
Alright, so an overview of our drivetrain, which is composed of 8 total motors, giving us 88 watts of total power. 4 of these motors are right along the bottom of the drivetrain, connected right in line, and the additional 4 are mounted on the back of the robot, using some gears that are tied in tandem with the main drivetrain. This allows us to drive pretty fast across the field and also keep up in pushing matches against some of the bigger 24 spots. Having this speed also allows us to climb bumps like the parking zone. Additionally, we chose our wheel diameter, which is the smaller of the two, because it keeps our robot a little bit more stable, especially when moving back and forth, and still allows us to climb over the parking zone pretty easily. A look at the descoring hook, which proved really helpful in competition matches. It has two states, a retracted state at the top, which allows us to stay within the 15-inch frame to meet the requirements of the 15 spot, and also ohms at the start of the match so that we know it's at the retracted position. When the match starts during autonomous, the hook is deployed, which stays within the 22-inch expansion limits and allows us to descore blocks, as you can see in this demonstration video. It allows us to push our blocks into the control zone and then also push opposing blocks out as needed throughout the match.
So, two more requirements for this program were 3 3D printed parts per robot and 3 machined parts. Starting off, we have the hook that has 6 designed 3D printed parts and 1 machined part, that big shiny hook up there. That big hook up there. Then our block handler, which has 4 3D printed parts and 1 machine. Keep in mind the design and parts numbers are averages in the robots, there's slight variations. The color sensor has 2 printed parts, the housing and the mount, as you saw previously. The robot structure has 3 designed 3D printed parts, including this 3D printed hopper structure. The intake flap has 17 parts. That was a lot of work. And 1 machine part, which is this axle that runs through here. That was an upgrade that we made after our first scrimmage. And our drivetrain has 2 3D printed parts on it. Now, for the overview of everything here, we have 30 designed parts on each robot and 3 machined parts, which I think is a little bit over the 3 required, but doesn't really happen too much. Cost summary. So about 83% of the total cost was reused on the robot. 5% was use member purchases for things like the color sensor and 3D printed parts. 66% of the cost was reused electronics, and 11% was due to static discharge issues on the field for our grand total of $4,300. Now, for Trevor.
This is a simplified version of the Gantt chart that we are working through for the year. So obviously we started with the project initiation, moved into our strategy and planning, where we were looking at different game strategies, moving into research and doing a little bit of design to kind of see what works for other teams, what kind of is impossible to achieve. And then we were able to arrive at the design that we wanted to go with, one design for both bots. And we were building and integrating that design before semester 1, where we were then able to kind of move into some more advanced prototyping and refinement throughout the course of the winter break, and then prior to the semester 2 kickoff and scrimmages, where based on the knowledge that we gained throughout those practice matches, we were able to further refine our systems. And we also realized that we needed some additional driver practice, which is what we've been mainly focusing on leading up to the competition, as well as developing our skill strategies. And now we are just waiting for the competition tomorrow, as well as delivering the final report before the end of the
first skill strategy. The main objectives of the skills are 1, to clear out both of the parking zones, 2, to clear out all 4 of the match loaders, to load the blocks into the long pole, and then ideally get a double park at the end. So to walk you through it, the first block will go and clear out our parking zone, swooshing to the right and moving over to its match loader, where the robot on the left will go directly over to its match loader. Both of those will be intaked and then scored at the long poles before they head over to the opposite side of the field and unload those match loaders, scoring them on the long poles as well. From there, the bot on the right will clear out the top parking zone, where the bot on the left will head right back to our parking zone for a park. If time permits, the bot on the top will head down and attempt a double park. Here is a look at this strategy in action. So you can see the bot clearing out the parking zone before heading over to the match loaders. The blocks are then scored on the long goal, and we do have color sorting off for the skills period so that we can just score as many blocks as possible without any hiccups during the sorting process. The opposite match loaders are then intaked and scored on the long goal, hoping to get lucky and get a control bonus based off of how the colors are scored. That bottom block will head down to this parking zone and run over and clear it out. And at this point, that bot would head down to the parking zone for a double park, and the other bot would also park. So, strategy.
So now for the guidance. We use the next inertial sensor to measure the heading of the robot, and then that'll align with the goal heading. Then in step 2, we have another PID loop that tells the robot to drive to the required position. In the software, it's a function that we call where we pass in the distance for it to travel and the heading angle for it to go to. There's a couple other things. So we have limit switches on the back side of our robots, so that when it backs into the long goal, it can tell it to stop, or we have motor stall detection, which takes longer, but it's a backup in case we miss. So that routine looks like this, where we start off with 1, where the robots will go to the loading tubes. Then both of them in step 2 will deposit their blocks in the long hole. And then they'll both, in step 3, drive to these middle blocks here. And because of random heading biases in the next inertial sensor, the robots will trace their path back, canceling out that error, and deposit them in the long hole as well. Since the left robot here tends to finish faster, we send that one over to a park right at the end of the autonomous period. And that all looks like this. So in step 1, both robots go to try and empty these loading tubes. And like how this block falls down and gets sucked back in. Step 2, both robots attempt to score blocks in the long goal. Then 3, both of them go for these blocks in the middle. And score them in the long goal. And then, just as we saw before, this robot will attempt to do a park right at the end. Now, with
average is 30 between.
Between both robots, yes.
Wow. Yeah. And on that, if you were to potentially redesign it, do you feel like you could achieve the same goal with maybe less 3D printing parts? I mean,
Yes, it could be simplified. There are some parts that could be reduced.
okay. Yeah, because I remember looking at it, it seemed like that each had kind of their own specific things, so maybe there was some paring down. Another question I had was, what type of op-amp did you use in your color sensor?
I didn't use an op-amp. I just used a comparator. It was like it's a SP version of the LM393. It's a push-pull comparator.
Oh, just a
Yeah,
straight
that's
up.
it.
All right.
I don't have any on front end. It's just resistors and the RGB diode.
All right, thank you.
Any other questions?
What was the biggest challenge you ran into?
We've had lots of challenges.
What was the one that you really liked?
Personally, with the color sensor I designed, it works great at convention. It was very difficult to implement it in the robot just due to variations in the way the block is intake into the robot. I overcame those challenges and increased the sensitivity of the sensor itself. Yeah, it worked really good. That's a nice thing. Good.
I'll add on that, the electronics, as we mentioned in the budget tab, the electronics are really finicky on the field. There's a lot of static buildup. We had several motors, a brand new frame. Parts just got, the ports became unusable, either unusable or variable enough that we didn't want to risk it in a match. And that just led to a lot of time spent replacing connectors, testing out cables.
So software took a little while to work out. During our first few practice scrimmages, we had a fair number of issues with that. At the moment, we're at about 3,000 lines of C++ code, which took a little while to work out all the bugs from.
How much, you mentioned the strategy earlier on. How much design, build, test were you able to bring back into optimizing your strategy? The things that you try, you might be saying, yeah, the strategy is going to be too difficult, too inconsistent.
So yeah, initially when we were kind of developing that strategy, we obviously started off doing research, seeing what worked for other people, what was possible. We initially had thought of doing a hoarding strategy where we have one big block, and his goal is just to essentially pick up all the blocks around the game field so that the other team is prevented from being able to score any of their points. But we realized that we were able, with this strategy, able to score a lot of those blocks before we would have the chance to pick them up, going with a strategy like that. So it was just mostly about the research and then testing the systems and then iterating on that.
Does it feel like you kind of tuned in on something that is reasonably optimal?
Yes. Yeah.
Because, like most engineering projects of this complexity, like there's a lot of open-ended questions, and you need to kind of dial in on what's going